This is the pre-exposure video on limits, and the idea of limits, really limits are the mathematics of calculus. We're going to start by looking at average velocity and build towards instantaneous velocity. So what does average velocity really mean? And average velocity is just a change of position over the change in time. So I'm going to write it like this: change in position over change in time. And hopefully you notice that this looks like a slope formula. And if we were looking at a graph of position by time, this is change in y over change in x, or the slope. So the average velocity, to actually compute it, we're going to look at the average velocity between 2 points. So if we have a velocity at this point in time, and then we take another velocity reading at this point in time, the line that connects, right, you only need 2 points to have a line. The line that connects those 2 points is called a secant line, right, from your geometry days. And the secant line is the line joining any 2 points in a curve. So the average velocity is the slope of the secant line joining the 2 points on a graph of a position function. So I want to write that out for you. So the average velocity, actually I may have it on the chart. The average velocity is the slope of the line. Here we go. The slope of the line joining 2 points on a position function, right? And that line is the secant line. That's the secant line that joins the 2 points. So if we were to have these 2 points, put a line through them as we did here, then the slope of that line is the average velocity. Okay. So if I were driving a car from Ursinus to home, a logical question might be, what's the average velocity? And you would have the example of 2 positions, you know, what your speed was maybe starting out in front on Main Street, and pick another point in time when you get closer to home and look at the average velocity between those 2 points. But what if I wanted to know the velocity at one point during the journey? And that's going to lead us to instantaneous velocity. But before we get there, I just want to do an example of average velocity so everyone knows how to actually compute it. So here we've got the position of an object moving along a line is given by the position function here, and you're asked to find the average velocity of the object over the interval 0 to 2. So the easiest thing to do here is, if you have a graphing calculator, you can enter that equation in and evaluate it. If you don't, you're going to have to do it by hand. So the average velocity is equal to the change in position over the change in time. So the change in position is going to be found by the function s is the position function, and the input to s is time. Right? So time is your independent variable. So I want to look at the average velocity between time 0 and time 2. So I'm going to evaluate s of 2, which is the position at time t equals 2, minus the position at time equals 0. And that's the change in position. That's your numerator. Your denominator, or change in time, is t2 minus t1, which in this case t1 is 0 and t2 is 2. So if you didn't have a calculator, graphing calculator, that you could put this function into and just get the value of it at 2 and at 0, you would substitute in. Right? So you would do it by hand as such. And I just want to show you where it's coming from, but certainly you can use your graphing calculator for ease of the numerics. But this is essentially what you need to do. Right? And all that I've done here is just put 2 into the equation, and here I put 0 into the equation. All over 2 minus 0. So if I do my arithmetic cleanly, I should get 60.4 minus 20 over 2, which is equal to 20.2. So that's your average velocity. And depending upon what the unit is, it would be, certainly if this is seconds or feet or miles, you would have a unit there, right? It's either going to be mile per hour or feet per second. Unfortunately, this textbook example didn't give you a unit that you'd be working in. Okay, so that's an example of average velocity. But again, if I was driving a car from a sinus to home, my car, and I wanted to know what the average velocity is, this is how I would do it. If I wanted to know the velocity at one single point, maybe in front of your sinus campus at the Main Street gate, then I would need to look at instantaneous velocity. So to build the theory behind instantaneous velocity, I want to look at an interval. And I'm going to look at the interval t0, t1, okay? And as t1 gets closer and closer to t0, the average velocity is going to approach the instantaneous velocity. So what's happening here? And I have a little graphic for you. So if you can see, right, initially here's t1 and here's t0. And I'm moving this interval. Grab a color here that's going to work. You're getting, initially this is large, and then it's getting smaller and smaller and smaller and smaller and smaller, right? So t1 is getting closer and closer to t0. Well, to find the average velocity, right, I take the change in position over the change in time. But as t gets closer and closer to as t1 gets closer and closer to t0, right, the average velocity is going to approach the instantaneous velocity. So let me write in formula what's happening here. So the velocity, or the instantaneous velocity, is a limit. In fact, it's the limit, in this example, t is equal to 1. The limit as t approaches 1, right, so the interval is 0 to 1. As t approaches 1, then the average velocity is going to be the limit as t approaches 1. I'm going to replace this with the definition of average velocity, which is s of t minus s sub 1 of 1 over t minus 1. So what happened here is your time got closer and closer and closer to 1, which was the initial, right? I'm sorry, t, this is t0, right? As t gets closer and closer to 1, right, this thing becomes a instantaneous velocity. So the average velocity is the slope of the secant line. Well, then what is how does the instantaneous velocity relate? And instantaneous velocity is the slope of the tangent line of the position curve. So let's look at this next. So again, here we're looking at another diagram, another graph, where we look at 2 points in time, and they're going to start out far away. So here we've got 2 points in time, and the position. So this is position and time, okay? And as that interval shrinks, right, the secant line through those 2 points gets steeper and steeper and steeper until ultimately, if we're looking at just this point, the slope of the tangent line to that point is going to equal the slope of the secant line. So instantaneous velocity is the slope of a tangent line on a position curve. So instantaneous velocity and hopefully this will help some physics students, is the slope of the tangent line of the position curve. So the secant line approaches the tangent line, and that's really what instantaneous velocity is. As the point of the secant lines get closer and closer together, the average velocity approaches a limit, and that limit is the slope of the secant, is the same as the slope of the secant line. As it approaches that limit, that becomes the slope of the tangent line. So I want to show you a technique for finding a limit, and this is known as the table method. And there'll be other techniques that I will teach you, but we always start with the table method because I think it's easier for students to understand what's happening. So if you want to take, we're going to stay with the position function again that we had earlier. So here's your position function. And I'm going to build a table, and I'm going to change the interval for the table. I'm going to look at an interval where time is equal to 2 to 3, and then I'm going to cut the time in half, and I'm going to look at it from 2 to 2.5, and you can see what's happening. It's going to go from 2 to 2.1, 2 to 2.01, 2 to 2.001, right? So t is approaching 2. So let's build the table and see what happens. I need to use my graphing calculator because I'm not going to do this by hand. I'm going to use the graphing calculator to complete the average velocity for each of these intervals. Right? So I'm going to look at it from all of those intervals. So from 2 to 3, I may do one more for you. Right? I'm going to look at the position at 3 and subtract from it the position at 2, at time 2. Alright, this will be the last one I do by hand. And again, that's divided by 3 minus 2. So for that interval, it comes out to be 5.5. So this is, let me grab a different color, 5.5. If I use my graphing calculator and I compute the average velocity on the next interval, I get the average velocity to be 7.95 using, actually I used Maple. Alright, and the next one was 9.91, and the next one was 10.351, and the next was 10.395. So I could continue to go on. I could build another one if I wanted to, and I did not, but I could. And I could add, another decimal place and look to see what happens. And I can continue this. Keep getting closer and closer to 2, but not equal to. When I do that, I can see that the limit starts to emerge. This limit looks like, and here's a guess, but I'm guessing that the limit appears to be 10.4 meters per second. So the limit appears to be 10.4 meters per second. In fact, I'm going to give you a Maple Lab that demonstrates the table method, and you'll be able to see for yourself what happens. So that's the idea of a limit. Okay? It's a pre-exposure, and we'll do some computations in class.